Hello to you all Ansys users and CFD enthusiasts. Welcome to CFD Land. In this video, we're going to proceed the part 1 and simulate the rest of the compressible flow investigation on a three-dimensional airfoil. And for those who haven't watched part 1, I suggest you to go back and try and watch the part 1 and then get to this new video in order to proceed the simulation. So until now, we designed the basic geometry of our model in Design Modeler software, and then via Ansys matching, we could generate a structured grid using 440,000 hexagonal cells in order to divide our domain. And the other information that are needed in order to proceed is about the compressibility of the flow, because the Mach number is 0.8. And in other words, we are simulating a transonic flow over this airfoil. Our basic, our section profile is NACA 0012, and the angle of attack of the incoming airflow is 4 degrees. So considering the configuration of our airfoil, we need to know that we have to do some really important steps in order to define the drag and lift coefficients, and also the behavior of our air as the working material is very important and can actually directly affect the results. Very well, guys. So you may remember in part 1, as our latest step in Workbench, we covered part 1, which is our initial step through the simulation, designing the geometry. Then we mesh this model with a structured grid, and then we transform it to Ansys Fluent as the solver. But for those guys who haven't actually followed us and don't want to design the model by themselves, they can download the MSH format file from our website, and then in the Fluent from File tab, and in Ansys Fluent standalone software, you can find it through the Read tab. Otherwise, when you're using Workbench, you can find Mesh into this import drop-down list. And then just by looking in the MSH format file, you can import it and start the rest of the simulation and follow us. Very well. So in General tab, the first thing that solver asks is the solver tab, which we have pressure-based option and density-based option. Of course, up until now, we haven't actually coped with a density-based solver because it is actually applicable for high-speed flows or where the density is not negligible. But considering the transonic flow, which means a high Mach number, maybe 0.8 Mach number, we can actually change it to density based. But regarding the convergence problem and also our accuracy, we can adopt pressure based solver. So you may heard that the pressure based solver is only used for incompressible fluids, but I need to add this, that for mildly compressible flows like transonic flows, we can adopt the pressure based solver and instead change our inclination and approach through the density term. So for now, I keep pressure-based solver, and then for time mode, we already know that we're going to investigate the results in a steady state condition, so there wouldn't be any need to change it. And after all, regarding the high Mach number, the actually volume forces like gravitational acceleration are not very effective on our results. So I neglect this gravity and get to our next step by expanding model section and double click on viscous. So in this tab, the software as always asks for the viscous turbulence model. Considering the high Mach number, we already know that the flow regime wouldn't be laminar, so of course we need 1 up to maybe 7 equation turbulence models. But in this simulation, we're going to adopt and employ a Spallard-Allmars one equation model. This actually one equation turbulence model used primarily for simulating aerodynamic flows around objects such as airfoils, wings, and vehicles. And it is actually best fitted for wall-bounded flows and more effective in predicting boundary layer behavior. And actually, based on Ansys Fluent tutorials, we prefer to adopt this model, and also we can keep the computational cost very low by using this. And there is one more thing that it may just bear in mind, that it is best suited for external aerodynamics applications, just such as this airfoil. So I keep this model and click on OK. So we may need to activate the energy equation, but because we're going to have ideal gas approach to the density, the software will automatically activate energy equation. So for now, I skip this part and jump to material section. In here, as you can see, Ansys Fluent has its own default materials, air and aluminum, and this actually is our process, so we don't need to change and define a new material. By double clicking on air, I have access to the actually a specification and properties of the air as a working fluid. So first thing is the density. As I mentioned, we're going to adopt pressure-based solver, but change the density approach in this simulation. Of course, in transonic flows, the density has actually slightly changes, and we cannot consider a constant density. Otherwise, we would have some errors in our results. So for this simulation, I'm going to use ideal gas law, and by adopting this method, the solver will actually calculate the density based on ideal gas law, as you can see in here. Then would be the time for the viscosity. Of course, considering the changes in pressure and also temperature, the viscosity wouldn't be and wouldn't remain constant anymore, just like the density. So this time, instead of using the viscosity as a constant number, I'm going to change this to a new method, which is called Sutherland. So as you can see in here, the Sutherland law has and have two different approaches. One is the 2 coefficient method, and the other one would be the 3 coefficient method. And in this simulation, I'm going to adopt 3 coefficient method and keep the reference viscosity, reference temperature, and effective temperature as the default values. You can read about these parameters more in Ansys tutorial guide online. Very well, so don't forget to click on change or create button and then close this section. So from now on, we consider the compressibility of the flow by considering a variable density approach like the ideal gas law, and also for the viscosity. And there is one more important thing in here that may worth mentioning, and it is the energy activation. As you can see in here, the solver automatically enabled the energy equation as required by material density method. Very well, so I close all of this section and jump to boundary conditions. And let's start from our inlet, which is called far field. So by now, as you can see in here, the software couldn't recognize the far field as an inlet boundary. So simply from drop-down list, you can select pressure far field from here. Very well. So as I actually mentioned in the introduction of this video, the Mach number in our model would be 0.8, and we know that this actually flow wouldn't coming in from a specific direction of X component. I mean, it has some components in different directions. It's not just in direction of X axis. So first of all, I put the Mach number as we wanted, and then we need to define the components in which that is satisfied the 4-degree angle of attack. So as you can see in here, we haven't designed the airfoil in a specific direction. So instead, we're going to apply this angle of attack to the components of the flow. So this time I wanna use the calculator in order to actually calculate the sine and cosine of 4-degree. So simply by using scientific mode of this calculator, I can put 4 and calculate the sine of that. So this sign component would be the y component of the flow. So I copied this and paste it in here. And of course the other component in x direction would be the cosine of 4. So one more time I copy that and paste it in here. Very well. So I wouldn't change anything else in here, and in thermal tab you can define the temperature of the incoming flow. Of course, regarding that, our actually concentration is on the fluid mechanics. This is not really important to me, but keeping it as 300 Kelvin would be enough. Next, it's time for the symmetry boundary. As you can see in here, these symmetry walls that are colored in yellow, and you can see on both sides, are like mirrors. I mean, there wouldn't be any perpendicular forces or velocity or normal component on them. So they will act just like a mirror, and this is actually the suitable assumption in this simulation. And our final boundaries are the pressure side of the airfoil and also the suction side. We call them separately in Ansys meshing, you may remember, in order to actually use them later in the post-processing step. So for now, let's just check them. These are just some walls, they are not moving, so a stationary wall is adopted by default, and the no slip shear condition is actually valid in this. And in thermal tab you would see that the heat flux is equal 0, or in other words, these all act like isolated walls. So I close this section. The same is applied for the suction side, and there wouldn't be any difference. Very well. So before processing to solution part, I need to mention one more thing in here, and this is the reference values. So maybe this is our first time that we're actually confronting the reference values in our free tutorials. You have to know that in order to calculate the coefficients, I mean the dimensionless coefficients, Ansys need to know some of these parameters in order to actually employ them in the formulas. So this time I'm going to compute my reference values from the pressure far field as our inlet. So as I select that, you can see that the software automatically detects the area, density, length, pressure, temperature, and also the velocity of the incoming air, and some more parameters. But what is more important in here, which actually related to drag and lift coefficient, is the viscosity, the velocity, the temperature, and above all of them, the length and area of our cross section. Considering 1 meter depth of our model and also 1 meter of the chord line, we know that the length is equals to chord line, and it is 1 meter, and also the area would be the projected area of our airfoil. So 1 multiplied by 1 would be resulted in 1 square meters. So I keep 1 just because of this, but considering your own case, you may need to change these two parameters. Alright, so let's go through the solution part. And above all of it, it's the methods tab. So in here, we've got 4 different choices provided by Ansys Fluent. And in this simulation, regarding the convergence of our model, I prefer to use coupled algorithm. So you may wonder what is coupled algorithm. Actually, it is employed for pressure velocity coupling scheme because it can solve the momentum and continuity equation simultaneously in a coupled matrix system. And this approach actually, it may be somehow computationally intensive, but it typically offers faster convergence, and this can enhance our actually simulation compared to segregated algorithms just like simple algorithm or piezo. And beneath here there is a section related to a spatial discretization for different equation and terms, considering the pressure gradient and the momentum equation, and two relations for turbulence, viscosity and energy. So for discretization of pressure gradient term, I'm going to adopt a standard model, and it is used for better convergence, but I'm going to keep second order affine discretization method for density, momentum, modified turbulence, viscosity, and also the energy due to its higher accuracy. Very well. So it's time for checking our convergence criteria. On most of the simulations, the residuals are known as the primary convergence criteria. Actually, in CFD simulations, these numerical measures of the imbalance or error in the conversation equation, and for each cell it is computed and reported in the console part during the simulation. But it may not be actually a guarantee for our convergence. So in this time, I'm not going to trust them. I'm going to monitor the drag and lift coefficient during each iteration and check it and monitor it by myself. So the simulation wouldn't be stopped by residuals. In order to deactivate these residuals, you can uncheck these boxes. So as the substitution, I'm going to define new reports for drag and lift coefficients and monitor them during the simulation. So from report definition part, by right clicking on that and define a new force report, you can find drag and lift right here. So let's start from drag. First of all, I'm going to name this report as drag co actually it stands for drag coefficient, and the report output type would be drag coefficient. So your software will adopt drag force on the airfoil or the zones that we are going to activate in here, and by considering the reference values, it can calculate the drag coefficient. But one more key and critical points in here is the force vector. As actually mentioned and shown in the introduction video and also mentioned in here, the force vector of the drag force is in the flow stream direction. So we already know that there would be 4-degree angle of attack, and we need to have different force vector components. So one more time, I have to use a calculator in order to actually have the sine of 4-degree. And this would be the y component of the drag force, and for the x component, of course, this time it would be the cosine of that. And simply as that, you can define the force vector of the drag coefficient, and don't forget to select both sides of our airfoil. Very well, so this was the drag coefficient. I'm going to repeat these steps, but this time for the lift coefficient. And notice that considering the 4-degree, we need to know that, and just notice that the cosine this time would be the x component, but it should be in negative direction. So I put minus and then paste the value. And this would be our x component, and also for the y component it would remain the same. Very well. So I guess we are done with the solution sections. It's time to have the initial guess through initialization section. I simply change the method to a standard initialization method, and in Ansys Fluent it sets uniform values for all flow variables across the entire computational domain. And by having the initialize button, we can have the initial guess and proceed to run calculation section, define an appropriate number of iterations, something like 1000, and start the calculation. So this time I'm not going to pause the video. We're going to see and monitor the drag and lift coefficient in each iteration. So you can see that until now they actually haven't reached a constant value. And these are the residuals. Very well, so let's check the results. As you can see in here, we've got a perfect convergence, and the actually main reason of that would be our solver settings, but more importantly it's about the structured grid. And as you already see, maybe by considering the primary convergence criteria as residuals, the solution has stopped earlier, but we can see that it hasn't reached convergence before 140 or 50 iterations. This is why I prefer to check it by myself and monitor drag and lift coefficient. And now you can see that the fluctuations are not wild, and we can see and stop the solution for post-processing. Alright, so as we saw that we have reached the convergence based on drag and lift coefficient, and let's have the exact value. From report definition part, by right clicking on each of your reports and click on compute button, you will have the exact actual value of the report in the console part. This is our lift coefficient, and this would be our drag coefficient. So considering all of this, I'm going to depict all of these results via using this contours option, which you can find by expanding the graphics section. In this window, the first thing that solver asks is the variable that you're going to illustrate. Of course, we can start from pressure, velocity, or temperature, or even some turbulence related parameters. So let's start from pressure. And beneath that, there is a section called surfaces that you can select a specific boundary to depict and illustrate the pressure distribution on that. But because I'm going to have it through all these sections, I need to create a two-dimensional section and put the pressure distribution contour on that. So this time I quit Contours tab, and let's get back to our General tab to display all of these boundaries to see what we're going to do. So this is our 3D model, and we're going to create a section plane exactly in the middle of our model. From Domain tab, follow the Create and then Plane. So I'm going to change the method from YZ plane into XY plane, considering the general coordinate system. And considering our scale, which is 0 to 1 meter in the direction of Z axis, 0.5 meters would be exactly in the middle of our model. And don't forget that this created a new plane is called plane 4. You can simply change the name, but I'm going to keep it. Now if I get back to Contours tab, in this time I can find plane 4 beneath the surfaces section. So I deselect all of these planes and simply click on plane 4 and then display it. Very well, so this is our pressure distribution around the model, and you can see how there is a shock on the suction surface of our model. Considering 4-degree angle of attack, it is actually natural, and actually the Mach number is very high, so we expected a shock on the upper surface of our model. You can also see the range of the pressure. It starts from minus 54,000 Pascal up to 52,000. You may wonder why it is negative. Actually, we are considering 1 atmosphere as our reference pressure. So considering a static pressure of minus values, it means that we are comparing it, and it is relative value to our operational pressure, which is 1 atmosphere. And then for the velocity distribution, we can actually clearly see how we've got a stagnation point exactly in the actually point near the leading edge of our airfoil, and it is not exactly in the middle because we've got 4-degree angle of attack. And we can also see the formation of the wakes here due to actually pressure gradient and shock that is happening here. But regarding the use of one equation as plot almost, we cannot expect to see full wakes around here. You can proceed this model with alias in order to have the large eddy simulation and see the large actually wakes forming behind and on the upper surface of our airfoil. But for now, regarding this one equation simulation, we can actually be satisfied by these results. But what is more interesting in here is that the boundary layer is starting to grow in here, confronting a pressure, an adverse pressure gradient that actually causes flow separation in a point somewhere around here. So this time I'm going to use vectors. It can help us in order to check the separation point. So simply I select plane 4 and apply this in order to see the velocity vectors. But these are just too big arrows, so I may need to change the 3D arrows to arrow to have 2D, and they just need to be scaled to have actually a smaller arrows, just like this. And you can see actually the growth of our boundary layer and how the flow is separated somewhere around here, around this blue arrow on the surface, and this is actually the exact place that separation occurs. So I'm going to do one more step in order to show you the plot of let's just say pressure distribution on both sides of our airfoil. So this time I'm not going to display all the boundaries. Instead, I'm going to just have the pressure side and suction side of my airfoil, just like this. So I'm going to actually cut these two surfaces by a specific plane, which results in formation of a line, or better to say a curve. And by using this curve, I can plot the pressure or shear stress on both sides of my airfoil. So this time from domain tab, I follow create and IsoSurface. So we know that by intersection of a plane actually perpendicular to these faces, the intersection point would be a line. So this is why I wanna choose mesh and then have a plane actually moving through Z coordination. So it will have intersection with pressure side of my airfoil, and it will be actually in the zone and the one and only zone of our computational zone. So as I click on compute button, the software will show me the minimum and maximum of my Z coordination in this or better to say along this surface and also inside this computational zone. So as you move this button, you will see that it is actually moving through this Z coordination, and it has intersection with these planes that we are selecting from surface box. So as I'm going to have it and create it exactly in the middle of my model, I want to put 0.5 meters. And notice that it is our pressure side, so I'm going to call this press line and simply create that. Another time I'm going to deselect all and instead select suction surface. And now let me zoom in, and now I'm going to repeat this process to show you. This time we're going to have it and have the intersection with the suction side of my airfoil. Very well. So this was the use of IsoSurface. Maybe you can find and use this tool later in your own simulations. So by having these two curves, I can jump to plot section and open XY plot. So in this simulation and regarding our need, pressure and shear stress can help us in order to analyze these outcomes and findings of our simulation. So I'm going to keep the variable as pressure, and instead beneath here, beneath the surfaces box, I want to choose the press line that we created, which shows us the intersection of two surfaces, which resulted in a curve on just pressure side of my airfoil. I'm not going to change the name of this plot or no matter the position of the x-axis. I'm just going to plot the pressure on my pressure side of my airfoil. And notice that this pressure distribution can be actually shown simultaneously by having this suction line. So this time you can see the suction line indicated by purple and the pressure line indicated by somehow green. And this would be my pressure distribution. And as you can see in here, along the suction line, we are experiencing a drastic change in pressure, which shows us the actually separation and also the shock that is happening on the suction side of the airfoil. And actually considering this coordination, we already know that this is happening somewhere around 0.3 meters up to 0.5 meters of my cross section. And simply as that, we can have the plot of different variables, but what I'm looking for in here is actually the shear stress, which you can find beneath the wall fluxes. So the wall shear stress can say many things to us, and it can actually shows us the exact point that the flow separation is happening. And by using these tools, you can provide many findings and outcomes in your report. So I guess we're done. There is no more thing that I want to show you, but it may just not be actually it can be beneficial to show you the path lines as well. So through this option, we can depict the path lines of our model, but notice that due to its high computational cost, you may need to increase the path skip first, and I just don't want to waste any time, so I simply select my suction and pressure side of airfoil to display the path lines. And these path lines can actually clearly show you the separation, the formation of wakes on the suction side of the airfoil. So I may need to decrease the path skip to have more path lines and also increase the steps to complete these path lines. Very well. So simply as that, you can see the beautiful wakes forming behind this airfoil. And at the same time, I'm going to draw the mesh of pressure and suction side so I can have them simultaneously in a section, or better say in a single view. And you can also use all of them for post-processing in your report.